Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on differential equations, and in particular I'm going to show you how to solve a special type of differential equation called an exact differential equation. Now you might see this in a course in differential equations or maybe in a calculus 2 course. Okay, so here is the example that we're going to look at. We have got a differential equation here. It's a first order problem because the highest derivative is a first order derivative. And we're going to solve this problem using an approach to what's known as exact differential equation. So let me just sort of call this function m and this function n. Now sometimes in these problems the dx is sort of connected with the m and the n is connected with the dy. I just haven't written it that way in this example to just to save a bit of space. Okay, so m is a function of two variables, x and y, n is a function of two variables. Okay, so when we're looking at these problems, is our ODE, our ordinary differential equation, is it exact? Now, what do I mean when I say exact? Well, for the m function and the n function, do we have the following equation holding? Now, the subscripts mean partial derivatives. So m sub y equals dm dy with curly d's. N sub x equals dn dx with curly d's. This kind of condition is known as a condition of exactness. Okay, so this is our exactness condition. So what we're going to do, we're going to verify this, and then we'll go through and actually solve the problem. Now, this is like a check to actually verify that the condition, the method that I'm going to show you actually works. All right, so let's compute those derivatives. So m sub y, so there's m. So let's differentiate this with respect to y. Remember, when we're doing that, we imagine x is a constant and differentiate normally with respect to y. So that'll become 0, and this will become 2x. What about n sub x, dn dx? Well, let's go up to here, differentiate this with respect to x, imagining y is a constant. So that'll go to 0, and this will become 2x. Okay, so we see that these two things are the same, and so this is our test for exactness covered. All right, so hence our ODE is exact. All right. Okay, so you're probably thinking, well, come on, how do I solve the problem? Well, this check that we've just done actually verifies that the procedure we're going to implement is a rigorous and a well-founded procedure. It won't work necessarily if you don't check that condition that we just checked. Okay, now what's underlying the method that I'm going to show you is the chain rule for differentiation. Okay, so let me show you that. All right, so what we're going to do, because we have this exactness, we're going to assume that the solution to this problem is in some implicit form. Okay, so we assume the solution is in implicit form. Say big F of x comma y equals c, where c is a constant here. Okay, All right, so we don't necessarily have the y function, the solution to this, out on its own. It's just wrapped up in this bigger function f. And what we're going to try to do is compute the bigger f. So let me just sort of flag here that c equals a constant. Okay, I've just sort of squished that in down there. All right. Okay, so from this, we're going to continue, and we're going to have the following. With the following, okay, so the partial derivative of f with respect to x is going to be this m function, and the partial derivative of f with respect to y is going to be this n function. Now, where do these two things come from? Well, differentiate both sides of this implicit form with respect to x and apply the chain rule or the implicit differentiation, and then compare what you get with this. This has got to be this. This has got to be this. Okay? All right, so what is m? M is 2xy plus 1. And n is x squared plus 3y squared. Okay, so what now? Well, we've got two partial differential equations there, which we're going to integrate and solve. Let me show you how we do that. All right, so we're going to integrate this thing with respect to x, and we're going to integrate this thing with respect to y. Okay, so integration yields the following. Okay, let me take a new piece of paper for that. All right, so what we're doing, we're going to integrate this with respect to x. So I integrate the left-hand side with respect to x. F sub x, or f df dx, will become f. So I'm integrating over here. All right, so I'm imagining y is a constant, and I'm integrating with respect to x, just from this thing here. Okay, if I integrate, I'll get x squared y plus x. Now, you might think, well, okay, I'll put in the constant of integration, but for partial derivatives, we don't want a constant of integration, we want a function of integration. A function that depends on y, the variable that we're not integrating with respect to. Because if you take the partial derivative of this with respect to x, this will become 2xy, this will become y, and this will become 0 for any g. Okay? All right, so that's the first part. Let's integrate both sides of this with respect to y. We'll get the integral of x squared plus 3y squared dy. Okay, so imagine x is a constant and let's integrate with respect to y. So this first term will become yx squared, and this second term will become y cubed. And again, I've got another function of integration with respect to the other variable, h of x in this case. All right, so we're making our way through the problem. Now what we want to do is compare our two last lines for the big F, because our goal here is to get an implicit form, an implicit solution form, by constructing this big F. So let me show you how that works. We want to compare, so F equals this, and F equals this. We want to compare these two, make them the same by choosing G and H appropriately. All right, so compare our F, and we're going to choose G and H so that They are identical. All right, so let's have a look. Well, I've got an x squared y there, and I've got an x squared y there. I've got an x up here, no more x's down here. And I've got a y cubed down here and no more y cubes up here, except for these two things. So if I make g of y up here equal to y cubed and h of x down here equal to x, I'll get the same expression there and the same expression there. Okay? It's a little bit subtle. Let me show you that again. Compare these two things. These two things are the same. Okay, so we can forget about those. They're in both of them. To get our x down here, we want to, which is up there, we want to make h of x x. To get a y cubed up here, which is down there, we want to make g of y equals y cubed. Okay, so now both of these expressions will become the one and the same thing, and this implicit form will give us the solution to this problem. Okay, so is the following. F is going to be, let's say, x squared y plus x plus y cubed. Equals a constant. Okay, so that is our implicit form of the solution to our original problem. Okay, all right, so the next question is, how do I know I'm right? It looks like a very complicated form of solution. Okay, how do I know I'm right? Well, I can differentiate it and check. So let's see how to do that. All right, so what I'm going to do is I'm going to take the derivative of both sides with respect to x, and hopefully I come up with something like this. Okay, so so we're happy about that. Sees any constant here. So let's check. Let's take the derivative with respect to x of both sides. And this is where the implicit differentiation, or the chain rule that I mentioned at the start of the video, comes into play. Okay, now obviously the derivative of the right-hand side is 0. What about the left-hand side? Well, we can split this up, and the first part is the derivative of a product. Okay, so, all right, so the product rule. The derivative of x squared times y plus the derivative of y times x squared. Okay, so the product rule will give us something like this: 2x times y, so that's d dx of x squared times y, plus x squared times d dx of y, which is just dy dx. Okay, what about the next bit? D dx of x is just 1, and d dx of y cubed, well, just applying the chain rule there, it's going to be the derivative of y cubed with respect to y times dy dx. So the derivative of y cubed with respect to y is 3y squared times dy dx. And we've got the 0 from the right-hand side. Now, I can put these derivatives together. So we get the following. We're going to get 2xy plus 1. We're going to bracket those up, and I'm going to put the derivatives together in one sort of bracketed case. Okay, now that's what we get. What did we start with? Da-da-da-da! Yay! That and that is the same, that and that is the same. So we're very happy. We have just verified that this form really is a solution to our original problem. Okay, so that was a pretty long method, but the take-home idea, the big picture, is the following. Okay, the idea really uses nothing more than the chain rule for differentiation. Okay, it's sort of hidden or implicit differentiation, if you like. Now, from a procedural point of view, let's just go through the steps again as one sort of final overview. All right, so the first question is our ODE exact? Sometimes the dx is up there, okay? And this condition here is the condition for exactness. If that holds, and that gives us a license to look for a solution in this form, we solve these two partial differential equations through integration, okay? And then we get over to a situation where we're comparing these two things, and we want to choose a g and a h so that these two things are the same. Now, what could happen if you don't check that condition for exactness? Well, I'm glad you asked. Let me show you. If you don't check this, then what might happen is you'll get to this case and you can't choose a G and you can't choose a H to make these two things equal. Okay, so checking that exactness condition is really important. Okay, hope you enjoyed this video. The motivation, of course, for studying these kinds of problems is applications. Differential equations are everywhere, and they describe dynamic processes and lots of physical phenomena in the world around us. Hope you enjoyed this video. Hope you tune in again for my forthcoming videos, again, streamed live. If you have any questions, if you're watching on a mobile device, I'm trying to gauge your experience. So if you are watching, please let me know what it's like. Thanks for watching. See you later, everyone. Bye.